So the next thing to look at in transition metals is a thing about the behaviour of the complexes that you form. One of the main behaviours you can look at is actually their appearances, because different complexes tend to have different colours in solution, which can be quite useful for identifying unknown metal ions in a particular solution. So one thing in USPEC to look at is to learn the different colours of the transition metal ions in aqueous solution. So you've got a table here in your notes on page 5. It's quite a long list, which is quite annoying, but these are the ones that they give you. So you've got chromium 3+, chromium 6+, manganese, iron 2+, iron 3+, cobalt, nickel, copper, and then 4 vanadium ions here, which all got their unique individual colours. I've changed them to make them up to date with kind of CA's most recent list of colours that they accept. One thing to bear in mind, apart from the fact you just have to kind of learn those off, is that when we're talking about these ions, it's not, again, as it looks in this table, as simple as just that ion in some water. Remember, these are complexes. It's just that giving the full complex makes this table look a wee bit kind of intimidating. What we really mean in this table is, if we take the first one example, we're saying it's a ion in aqueous solution. That means we're going to form the aqueous complex, which in most cases, if not all, is going to be the metal ion with 6 waters. That's the most common coordination number with water, with the overall charge, sorry I've written that wrong, the overall charge of 3+ on this side of it. So that's kind of what we mean for all of these ions in this table. You just normally just give the ion to make it look a bit clearer. But you've got different colours for different ions. So I said that can help you identify unknown ions, but it's not perfect, as you might even just scan down the table. You have got some ions which have got overlapping colours. For example, chromium 6+ and iron 3+ have similar colours. You may also look at iron 2+ and nickel 2+ are both kind of shades of green. So we do need a kind of better way of identifying ions apart from each other. The main way we do use is to form precipitates. Now precipitates, if you remember, are solids formed by the mixture of 2 solutions. So we've seen that before in terms of like silver nitrate tests, Feeling tests, things like that. We can use that in this case to work out distinctive colours of precipitates to help us identify distinctive metal ions. How we form precipitates from these metal ions in aqueous solution is we normally add alkali to them. The alkaline complexes tend to be quite insoluble in water, so generally they form precipitates. So we're going to look at the sodium hydroxide precipitates first, which is one alkali precipitate you can form, and then second of all the ammonia precipitates, which are very similar but have some slight differences. So on the next page of your notes, you will have a table. Now it's a slightly smaller table, they don't give you quite so much information to learn off for this one, of 7 metal ions and how their precipitates might form with addition of dilute sodium hydroxide, see at the top there. So I'm going to fill that in for you, and this is what we end up with. So for these 7 ions, in the first column we've got what they look like just in aqueous solution. So before we formed any precipitate, if you have these ions in an aqua complex, they have these particular colours, as we saw on the previous page. So if you add sodium hydroxide, and just a small amount of it, for all of these metal ions you'll form a precipitate. So for chromium 3+ you get green blue, manganese you get a white precipitate that turns gradually darker over time, Fe2+ goes green, Fe3+ goes brown, cobalt 2+ blue, nickel 2+ green, copper 2+ blue again. So you've got distinctive precipitate colours, well kind of distinctive, for each metal ion. Now on the right hand side we've got an observation. For some precipitates, if you add a wee bit more of the reagent, for example more sodium hydroxide, the precipitate might redissolve. For sodium hydroxide, it's not a huge phenomenon. It's only actually the chromium 3+ which redissolves, dissolves again. So the green-blue precipitate from chromium 3+ will dissolve to form a green solution if you add extra sodium hydroxide. All the rest don't actually change. You'll just form more and more precipitate as you add more sodium hydroxide. Now, so one thing just to look at is just the idea. It's a list of colours to learn off. So just knowing for iron 2+ you have a green solution forming green precipitate, that's easy enough to kind of learn off. Be helpful to have a little appreciation of what actually is going on here to form those precipitates. So if I take, for example, iron 3+, if you have an idea of what's going on here, at the start, when it's just iron 3+ dissolved in water, you've got an aqua complex. So if I have 6 waters around this, I'll have my hex aqua complex, which I should have. I'm going to draw it a wee bit differently with the waters actually showing their structure. So you've got the oxygen with this lone pair donating electrons to the empty d orbitals of the iron 3+. So that's my aqueous solution of iron 3+ ions dissolved in water. What I've added to this solution is sodium hydroxide. Sodium hydroxide obviously is an alkali, more specifically it's a base, and bases like to take protons away, take away H pluses. Obviously with the water ligands here, you've got a good source of protons or H pluses because all these oxygens are bonded to the iron, giving a lot of electron density to that iron in the centre, which is going to weaken these bonds to the hydrogen a wee bit. So what your OH minus ion can actually come and do with its lone pair is come in, remove that H plus and leaving you with an OH ligand at the end. So if I do it 6 times, now it's not necessarily going to do it 6 times, it might only do it a few times, but just to give you one extreme, what you could actually have is all of the the H2Os losing an H plus by the hydroxide ion taking taking a proton away. That will leave you 6 OHs as ligands, more specifically the hydroxide ion. In this case I have 3 minus because your OH has got minus charge. That's only a slight change in that structure. You just remove an H plus from all these waters, but it is now a completely different complex. That's 6 waters attached to the iron, this is 6 hydroxides attached to the iron. And what we find is, in most cases, when you've got hydroxide complexes as opposed to water complexes, these are much less soluble in water, leading you to form precipitates depending on the colour depending on the particular metal ion in the centre. What can happen though is that some of the hydroxide precipitates actually do become soluble again when you've got enough of them. So with chromium, the reason it redissolves is that the chromium with 6 OHs is actually an aqueous solution. It can dissolve. All the rest of them can't actually dissolve no matter how much sodium hydroxide you add to it. So when you add sodium hydroxide to a metal ion, you generally form a precipitate with a particular colour. Whenever you add extra, in some cases, though in this case just one case, you actually get that precipitate dissolving again to form a solution. There is an other type of base you can use to get precipitate to form, and that is ammonium solution or ammonia solution. It's pretty much the same, but there's a couple of wee differences. So you've got a similar table on page 8, you've got the same metal ions, you've got the colour of the aqueous solution, and then observations when you add ammonium hydroxide, which is just ammonia solution dissolved in water. So with that table filled in, it looks pretty much the same. So you've got the same aqueous solution colours for these ions, so just dissolve the water before you add any ammonia to it. When you add some aqueous ammonia solution, what you notice is that the precipitates you form are identical in appearance. These are the same colours you've got on the previous page of your notes. Now the reason they are the same, despite the fact you're adding a different reagent, is that the reagent's doing an identical thing. Ammonia in solution is just a weak base in the same way that sodium hydroxide is a strong base. So it's going to do exactly the same thing. It's going to remove protons from the water ligands, turn them into hydroxide ligands, which end up being insoluble in water, giving you these precipitates. There's a slight change in the final column though. Whenever you add some extra sodium hydroxide, so more than just a few drops, add quite a lot of it, the pattern of how the precipitate dissolves is a wee bit different. So whilst chromium 3+ did dissolve with extra sodium hydroxide, it doesn't with extra ammonia. And same with manganese, iron 2+, iron 3+, there's no change when you add extra. You do get a difference with the cobalt, nickel and copper precipitates though. They do dissolve with extra ammonia solution. Cobalt goes to yellow solution, nickel goes to blue solution, copper goes to, probably should say a deep blue solution. Giving you another way of identifying them. Now, in terms of why that takes place, because that's a little bit harder to understand, because again, I've just said that ammonia is just another example of a base. You get something a wee bit different in these cases. The difference with ammonia solution compared to like sodium hydroxide is that ammonia in itself is a ligand. NH3 can bond to metal ions. And with these 3 cases down at the bottom of cobalt, nickel and copper, why you actually get solutions forming is you actually get a different complex forming. If I just take one example, though it's the same for all 3, or pretty much the same for all 3. If I look at cobalt at the minute, when it's precipitate, is some kind of variation of cobalt with water molecules and some hydroxide molecules. Again, we're not quite clear about how many we've got. It doesn't really matter too much. But let's say 2 waters have lost a proton to form hydroxide ions. So we've got 4 waters left and 2 hydroxides bonded. So that would be my precipitate. When I add lots and lots of ammonia though, I can get some ligand substitution, which we looked at earlier. Ammonia is quite a strong ligand. It can displace the water and the hydroxide. And what we end up with is cobalt with 6 ammonias attached to it. And it just so happens that that cobalt ammonia complex is soluble in water. So that's what's going to happen with cobalt, nickel and copper. That's why they go from being precipitates to solutions. The complex is actually changing. The ammonia you add is no longer acting just like a base. It's now acting as a ligand, which can bond to the metal ion and form a new complex which is soluble in water. So you've got a little bit of understanding to get in your head about why you've got precipitates forming in terms of losing protons from water molecules, and also why you might get some redissolving to form solutions depending on forming aqueous solutions of hydroxide complexes, or displacing in this case and forming ammonium-based complexes. The last little thing on colours to look at is, and this is the last little thing in the booklet, is on page 9 and 10. It's to do with vanadium. So we have a little subsection on one transition metal ion by itself, and vanadium is what we look at. It's quite an interesting transition metal ion. It's interesting because it's got a number of stable oxidation states. It's stable from +5, +4, +3 and +2, so quite a large range. And each one of those oxidation states has a different colour solution to it, which is quite interesting to look at. So I'm going to skip just forward onto the back page, where you see this table. So this describes the different ions you've got with different oxidation states and the colours of them. So as you see, you've got vanadium. It's a bit confusing looking. That's vanadium brackets 5, so the oxidation state is +5. So vanadium +5, a slightly different vanadium +5 we'll look at in a second. Vanadium +4, +3 and +2. So that's your different oxidation states. Each of those have got different colours in solution. Fair enough. The reason we've got 2 ones with a +5 oxidation state is whenever you actually have vanadium +5, it generally is found in this form. Vanadium bonded to 3 oxide ions, so VO3-, and you work that out, it's got +5 on the vanadium. It's not particularly reactive in that form, no. If we introduce it into some acidic conditions, it actually converts into this form, the VO2+ ion. So it's vanadium, 2 oxide ions, overall plus charge. It's still a +5 oxidation state for vanadium, but it's a bit more reactive. So that's one we'll look at. It's also got a colour associated with it. The first vanadium ion is colourless. VO2+ actually is a yellow colour. So if we're able to convert from vanadium 5 to 4 to 3 to 2, we should see a number of colour changes. How we actually see that change is by introducing a reducing agent, because remember +5 is quite oxidised. As we go down these steps, we're getting gradually more reduced. Normally what we use to reduce vanadium oxidation states is a mixture of zinc and hydrochloric acid. It's nothing too complicated there. Zinc will basically give up electrons to form zinc 2+ and 2 electrons. Under the action of hydrochloric acid, these electrons produced will go to vanadium in order to reduce it. And as simple as seeing the colour changing as it takes place, from yellow to blue to green to violet. The other thing to look at with that is you could potentially have to give balanced redox equations for those changes from vanadium 5 to 4 to 3 to 2. So just give them to you at the bottom of this page. So if we're giving the change from +5 to +4, we're going from VO2+, that's the reactive form of vanadium +5, going to VO2+, very slightly different. So again, I'll follow my normal steps for balancing a redox equation. The change in oxidation state, this is +5 vanadium, this is +4, therefore it's a reduction of 1, which needs 1 electron. To balance out my charges, I've got neutral on the left hand side, plus and minus, I've got 2+ on the right, therefore I need 2 H+ to get the charge balanced. On the right hand side, I need a water to balance out the H's and O's. For +4 to +3, that's the VO2+ I've just made can be reduced further to make it go to this V3+. Again, that's a reduction with 1 electron. To get the charges balanced, I need, so I've got 1+ over here, 3+ over here. I need another 2+ on this side, 2H+, and another water to get that to balance out. Final change is the simplest one, +3 to +2. I've got vanadium 3 plus going to vanadium 2 plus. That simply just involves the addition of a single electron.